to do some work on the cross product. I mean, we covered a lot. I get a feeling it went quite well, but I could be wrong. So if I give you two vectors, let's just do this as an overlap. I'll just pick two vectors, A and B, and we'll talk about how you'd calculate the cross product, just to get into the swing of things. And then we'll start doing some stuff, not just calculating them, but actually doing things with a cross product. So, oh, I'm always picking ones up. Kathy, give me a vector for A, whatever you feel like.
12, 3, and 7.
Okay. Noah, give me a vector for B.
How about 3, 9, and 8?
You're only doing this because you know I'm going to make a mistake. You know that? Anyway, here goes. It's I, it's J, and it's K. And the vectors are 12, 3, and 7. And the second vector is 3, 9, and 8. And it's so many I's, take away so many J's. I know that is so easy to forget. The number of people who, especially in tests, forget that, that subtraction in the middle term. And then add the third guy, K. Okay, here goes. My pen's out here. Cover up that guy, and what do you get? 24, take away 63, not risking it. 24, take away 63, and the answer is negative 39. Do the middle one now. 96, take away 21. I get 75. Last one. 108, take away 9. Well, 99. So our answer will be negative 39, negative 75, and positive 99, I hope. Now, this is a WebAssign issue. WebAssign might be asking you to give the answer in this format. And you might be wondering, how do I get the funny little I, J, and K guys? Well, in WebAssign, these are bold I, bold J, and bold K, but do not use a keyboard. It does not work. You have to do, let me show you where you have to go and do it, although hopefully you've already discovered this. Suppose I was going to put an answer in here, and I needed it to be I, J, and K. Hopefully you're all looking at WebAssign homework questions, right? You click on the vector guy. Do you see the I, do you see the J, and do you see the K? So if the answer was negative 39 I, negative 75 J, plus 99 K. Now, do you know, it just looks like the letters I, J, K on your keyboard, but they're not. It's specific to that place, right? You know the little vector with the hat on it? That's this guy here. So can you imagine you had a question when you had to do AB? That's how you would get that done. Do you recognize the funny little, the ones I like, in which case the answer would be negative 39, comma, negative 75, comma, 99. Are we all comfortable about how you need to hit the vector thing on your little calc pad when you do vectors, essentially, right? Because you'll look at it and it'll look perfectly correct, right? I did I, J, and K, but it was a keyboard I, J, and K. It's not that clever. It'll just say you're wrong, which is annoying. I'm assuming most of you have kind of noticed that, but just in case you haven't. Right, so let's return now to what we were doing. And this would be the answer, or this. I'm not sure. If WebAssign is being nice, either answer will be correct. If WebAssign is being awkward, they might want you to write it this way, or they might want you to write it that way. My suspicion is that if it doesn't allow both, if the question looks like this, they want the answer to look like that. If the question had 2i plus 3j plus 4k kind of look, then they'd want this version, right? That's what my guess would be. So if you're sure it's right, but it ain't taking it, it's probably the other version that you need. So are we cool? If I gave you any two vectors, A and B, with numbers, you could do them, no problem. Okay, so let's look at a version question 15 where we get to do things with cross products. We have the point P with coordinates 2, 0, 2. We have a point Q with -2, 1, 4. And the guy R 3, 2, and 6, at least in my example. And question A is phrased, find a non-zero. And that's just there because the zero vector screws up every calculation. So find a non-zero vector orthogonal to the plane through the points PQR. Now, sometimes the problem is figuring out what you're being asked to find, not actually getting the solution. So can you imagine that this is in 3D? If you have 3 points in 3D and there's nothing weird going on, which is what the non-zero vector is also about, don't you make a little triangle? And don't those wouldn't that triangle form a plane? Right. In other words, if you imagine a plane, a piece of paper, in fact, imagine that was there. Can you see if I bend my piece of paper, there's a plane, right? We want to find a vector that is orthogonal to this plane. That is another way of saying that we want a vector perpendicular to PQ and PR. Do you see how I've transferred that into a cross product problem? We are trying to find that. Now, I chose PQ and PR because I felt like it. If I decided to do it over here, which there's nothing wrong with that, wouldn't it be QP and QR? And if I wanted to do it here, which I'm not going to because it would mess in my picture, wouldn't it be RQ and RP? Now, you might say, well, what would I end up with different answers? Well, yeah, you might, but not majorly different. Do you know the only difference is they'd be parallel to each other, just maybe slightly different multiples. And since WebAssign is, I'm assuming, clever enough to cope with that problem, we don't need to worry about it. But I would just pick P because it's the first letter of the alphabet. Well, I need to know who PQ is and then who PR is. So if I cover this guy up, remember how you get a vector joining two points, isn't it? Second coordinate, take away first. So let's see what that gives me. -2 take away 2, 1 take away 0, 4 take away 2. Are you all happy about how I got PQ so quickly? Second coordinate, take away first. Second coordinate, take away first. Second coordinate, take away first. Now, if I want to do PR, 3 take away 2, 2 take away 0, 6 take away 4. Sorry, 6 take away 2 gets you 4. Are you comfortable about PQ and PR now? Okay, cross product coming up. Going to be an I, going to be a J, going to be a K. I hope a lot of you are calling it J now. Or at least when you do the homework, do you hear the letter J in your head? Kathy, Noah are nodding. Noah, you want to share this? Do you hear a little Scottish voice when you're doing your homework?
Sometimes, yeah, I do. I'm not gonna lie. I think what would Professor Robertson do, and then the Scottish comes in.
Okay. Kathy, what about in your brain? Do you want to share? Do you hear a little Scottish voice or just Jai?
I just hear Jai.
Just inside your, so you're fighting it. You keep correcting yourself? Or there's a new letter of the
I
alphabet.
roll with it. I still say Jai now when I'm writing it, but I don't call it Jai to my husband.
Oh, I think that's funny. Too busy talking. There we go. I Jai K. Okay, cover this guy up. What you get? 4 take. Oh, that's interesting. 4 take away 4 is 0. Negative 16 take away 2 more is negative 18. And negative 8 take away 1 is negative 9. So we are looking at 0, 18, negative 9. So the question was, find a non-zero vector orthogonal to the plane, and this would be your answer. Are we good with this so far? Now, there's a part B to this question, which we did touch on yesterday. And this one is asking us this time for the area of the triangle PQR. And I mentioned that if you take the cross product, which in this case is that guy, and you find its magnitude, what's the magnitude of the cross product going to give me? Just the magnitude right now.
The magnitude is the area of the rectangle?
Well, the parallelogram, but yes. So how do you get the area of the triangle?
Divide by 2.
Right. So a half of that guy. So I'm going to get a half of the magnitude of this fella, which is 0 squared, add 18 squared, add that guy squared. This is not going to be pretty. 18 squared is 324 because that's nothing. Add another 81 and I'm going to get, looks like 405. Doing a quick check here, which can be written as 9 times 45. Shouldn't that be 81 times 5? It is. So it can be written as 81 times 5, which means that it is 9 root 5. Okay. So as the simplest exact value, because we don't want decimals in these questions. Don't do decimals unless you are told to give your answer to 2 decimal places. The convention is exact value. So that guy ends up being this guy, which now becomes that guy. Are we cool? Anything about that? Are we good to move on? Question 14, which I'm not going to do, gives you 3 points. No, forget it. 14's 2D. I'm not doing 2D. I'll kick that one out. Yay. This is like 16. We're going to find the volume of my parallelepiped guy. And it's P. This is the coordinates of P. Here is Q. This is going to be the coordinates of Q. This is R. And finally, this is S. Now, I'm making no attempt to be accurate here, but can you imagine P goes here, Q goes here, R goes here, and S goes here. And that's the parallelepiped that they're talking about, right? So you need P, Q, and R kind of gives you this, and then another dimension is S. So I'm not going to do the entire details to this, but to get the volume of a parallelepiped it's a triple product, right? It's a cross product dot a vector, right? So what we've got to figure out is who goes who. So I'm going to find PQ cross PR. So PQ times PR. So essentially I'm focusing on this parallelogram. And then I do a dot product with what other vector?
PS.
And that's the guy that's going to get you the volume. So can you imagine finding vector PQ, PR, cross product, pretty much like we did a few minutes ago? You get that answer as a vector, dot product with whatever PS is. So for instance, PS would be, P to S would be second takeaway first, second takeaway first, second takeaway first, would be that guy. And I don't know what PQ and PR are, but won't we do this stuff and we'll find out? And can you imagine, just for argument's sake, it was 1, 2, 3? Wouldn't the dot product then give me the volume? Let's pretend we did this, right? We really did calculate it and it was that. Then in this case, the answer would be, so that would be -2 add 12 add 9, which is, I believe, 19. And the answer would be, the volume is 19 cubic units. But in a different world, couldn't it be -19? Different numbers. What is the answer to the volume of the parallelepiped when that triple product is a negative number?
The absolute value of that number.
So you make it 19, right? So you do exactly the same calculation and just wait until the final number pops out at the bottom. If it pops out as 19, great. If it pops out as -19, call it 19. If it pops out at 0, what does that tell us?
Coplanar.
It tells us it's coplanar. So the question will probably be not what's the volume of the parallelepiped, it would be, are these points coplanar, right? Are P, Q, R, and S coplanar? Now you're still going to do the triple product, right? But you're going to be on the lookout for 0. Now in those questions, the answers are yes or no. And you're not going to do, I'll pick yes, and if it's right, move on. And if I pick no, I'm just going to call it yes. Because you're not really practicing the process, right? You're just guessing, and guessing the other one if it's wrong. So that's how you do a volume one. Now, question 18 was pretty much that problem. I'm going to rewrite you. It's in terms of I, J, and K, but I'm just writing it down in its component form. So this is question 18. U is this vector. V is this vector. And W is this vector. And we're being asked, are they coplanar, right? Are these three vectors all in the same plane? Or is one of them sticking up? So the answer is a yes or a no. The test for it is a triple product. If the answer is 10, no, they're not coplanar. If the answer is 0, yes, they are coplanar. And 10 is an example. It could be any number you like, right? 42 minus 10. Now, you might say, why did you do U cross V dot W? Is that important? No. Do you know if I did U cross W dot V, right, I just mixed and matched them. Do you know that would get you the exact same numerical answer? Seems unlikely, but it does. And so if it's 0, it's still 0. The only minor difference, and I should correct myself, sometimes it'll be negative 10, not 10. That's just basically the orientation issue, right? So pick any letter, order you like. If they gave you P, Q, R, and S as coordinates, wouldn't you just find P, Q, P, R, and PS and use them like they were your U, V, and your W? And it's helpful to pick one fixed letter and then project to the other 3 points using P as your start. That way you don't end up actually doing an unusable combination of vectors. We cool with it? I'm going to call this one good. I'm just doing a quick scan in case there's anything I've missed. Well, I'll tell you what I'll do, because I've done this before and I find things I didn't cover. Let's have a quick look at what the homework looks like. Now, there's one question that sneaked in, which was a two-dimensional one, which I'll make sure I rub out sometime later today when I have time. So, here are some conceptual questions. And it says, state whether each expression is meaningful. In other words, can you get an answer to it? And if the answer is yes or no, then you have to choose one of those. Could you get A dot B cross C? Could you calculate that? Yeah. And what would you get if you did it? Would it be a number, which we call scalars, or would it be a vector? What would A dot B cross C get you when you're finished?
Scalar.
Scalar, right? You get 42. So in this list, the expression is meaningful. It is a scalar, right? Okay, how about C? A cross B cross C. I think actually we talked about this yesterday, where you could do a cross product like this. Could you get an answer to that? Yes. What would your answer be? A vector or a scalar?
Vector.
A vector. So it is meaningful and it's a vector. Now what about D? A dot B dot C, right? The dot product of A with the dot product of B dot C. Would you be able to do that? Would it be meaningful? No. Won't
No.
B dot C get you a number? 42. Right? Dot products get you numbers, scalars. You can't do a vector 1, 2, 3 dot product with the number 4. Don't you need vector dot product another vector? So it is not meaningful, right? And here are some conceptual questions. Whether or not these are true. So yes, it's true, or no, it's not. If A dot B is equal to A dot C and they're covering themselves with nobody's a zero vector, right? If A dot B is equal to A dot C, does that follow that B and C have to be the same? What do you think? Well, they both have an A, right? It's the second guy.
Yes.
Any votes on yes? Anybody think it's yes?
Yes.
Good, because it is. You can check it out. Is it possible that A cross B and A cross C, does it follow that they are equal? No. I could find a vector A and a vector B with its normal going one way, and then I could do a vector A and a vector B, and it's got the same normal. All right, that normal just means a cross product, right? Get the same cross product, and they're not the same. And
Wait,
there's a
did
little
you
video.
say- Did you say yes for the first one, for 2A?
For 2A, I'd say yes, and 2B, I'd say no.
It
Can it
doesn't
be,
like that
will it
answer.
be no?
Is it not?
Because, yeah, you're
Both
Oh,
say
adding,
no.
that's why it doesn't like no.
It doesn't like no for A.
wait, what?
Oh. Well, but A is yes, and B is no.
I mean, no, it doesn't like yes for A. Sorry.
What?
Let me try that. Okay. You're doing it with me. I don't get to get answers. I just type things in and it ignores me because I'm not a student, so I don't have the same version as you. Okay, let me try and prove that. If A dot B is equal to A dot C, does it follow that B equals C? And I'm saying yes, it does. So that would be A dot B, take away A dot C, would have to be 0. Okay? And you can pull out dot products in the same way that you can pull out common factors. And I have a dot product that's equal to 0, and this isn't 0. Ooh, this isn't 0, and that could be 0. You're right. I take my answer back. There are lots of ways where you could get 0, because I mean, A could be 1, 2. Couldn't you just make that 2, -1? But couldn't you also make it that one? Yeah. So it's not that they're equal. It's that they are, plus or minus of each other. So there could be a situation where it's a negative. So I was wrong. They are almost yes, but the answer is it could be plus or minus. So it could, if one of them could be 1, 2, the other could be -1, -2, for instance. Okay, I take that back. I'm wrong. I was almost right, but that doesn't count. Cross product. Do you know these little checks at the end? I mentioned them yesterday. If you want to save a whole load of time, can't you just say 0 and 0? If you did it right, it will be, won't it? In a test, I would probably do that just to be 100% sure you got it right. But in homework, you don't want to do it 20 times, right? Cross product, cross product, cross product using ij's and k's. And none of these you can see because I forgot to switch over and nobody told me. I'm lost. Where are we? Here we go. So anyway, you've got a whole load of cross products. That's question 4, 5, 6, 7, 8, 9. Here's question 10, cross product. Oh, this one's interesting. In question 11, you're doing a cross product of A and B. And let's just say, and this isn't the right way to type it, but it is, well, actually, I'll make it the right way to type it. That's me being lazy. Can we imagine that the answer is 1, 2, 3? just for argument's sake. What's the answer to B cross A going to be if I do it correctly?
Negative numbers of those.
Yeah. It's probably a good idea just to do that question, just to convince yourself. Can you see that what's happening in question 12 and question 13 is that instead of dealing with numbers, won't you be dealing with 1, e to the t, e to the negative t, and then the last row will be 5, e to the t, e to the negative t. Be careful when you multiply e to the t with e to the negative t, because something really nice happens. What happens if you multiply e to the t with e to the negative t?
They cancel out.
And you get 1. So there'll be a lot less e to the t's in that answer than you might have thought. This one here is just going to be some downright ugly t squares and t cubes and stuff.
It actually cleans up pretty nice.
It does. Oh, is there this cancels and combines with this? And oh, well done. Weber-Sein found a good combination. 14, area parallelogram, that one's gone. Why is that gone? It's a 2D question and we're on 3D vectors. So I accidentally put in a 2D question when I didn't mean to. So you might have done 14, but don't worry about it. It's going to go if you haven't. Oh, okay. Here are 3 vectors. Find unknowns. Oh, I've already done that. Yeah, it's just another reason to find a cross product, right? That's the one we did at the beginning of today. There's my parallelepiped guy. There's another one, but this time with coordinates. We talked a little bit about that one. And here's just a boring, are you coplanar? I think we probably covered everything there, right? There's nothing that I haven't looked at. So let's get started on our last section. So we are, or I will be in a minute once I figure out where the heck I am. Hold on for a second. Okay, go home. We're going to be looking at equations of lines and planes in 3D.
Right now we're looking at your desktop.
That's fine. I'm still trying to find the section. It'll be moving it. Coming up. Here we go. It's 12:05. But thank you for telling me that. Here we go. So let's return back to our notes and see what is in store. We are going to, I'm going to give you the intro to this, and then tomorrow we can get into the nitty-gritty. So it's the last thing in chapter 12, I believe. And it's equations of lines and planes.
Aren't we in 163? Not 152?
Yes, you are. I'm already thinking of what I'm going to talk about while I'm writing. Not a good idea for me to do that. Okay. In 3-dimensional space, you can still have a line. Right? Only that line's not a flat line. Isn't that line a line probably sticking out of the paper, right? It's like this. So when you see this, we try and imagine it's this pen, right? Now, equations of lines. In 3 dimensions is quite different from how you would do an equation of a line in 2D. Now, if I was doing an equation of a line in 2D, wouldn't it probably look something like that? The y coordinate is 5 times the x coordinate plus 1. And that would represent, I don't know, a line, something like that, right? Goes on forever. But in 3 dimensions, this doesn't work anymore, because don't we have an X, a Y, and a Z coordinate? So any point on this line, any general point P, will have an X coordinate, a Y coordinate, and a Z coordinate. And so how do we describe all the points on a line in 3D? And the way we do it is we use parametric equations. Something like this. But those parametric equations are typically going to be linear, right? So 2t plus 1, 3t minus 2, that kind of look to it, right? Not t squared minus t cubed. So far, so good. Now, can you imagine then for any given value of t, won't you get a unique x, y, z coordinate? The added advantage is that when you do equations of line in 2D and you use parametric form, that we condense this into a notation that looks like this. Isn't this essentially the same information? Would you agree? And this is very often called the vector equation of the line.
Is that an F in front of the T or a special?
It's an R. It's R like in Robertson. Although I don't get credit for it. Why is it R? I can't honestly tell you. If I was making it up, I would call it L of T, right? L for line. But I ain't the guy who does it. It's pretty consistent throughout most textbooks. In fact, I can't think of a textbook where it's not called R of T, but there probably is one. So it's a kind of convention that everybody likes to use R. So that's fine. You can do it too. So far, so good. Now, I haven't told you where you get these, and that's to come later, just getting the general idea. Now, if you think of T as time, it's very helpful. Because can you imagine this is just an aircraft flying in 3-dimensional space? And when you plug in T equals 0, isn't that where it is at the start? And then T equals 1, where it'll be 1 second from now, and T equals 100 is where it'll be in 100 seconds from now. And you can even argue that T equals -10 is where it was 10 seconds ago before you even saw it, right? Where it was in the past, right? So this line goes on forever, and this might be at T equals 0, but it doesn't necessarily have to be. So far, so good. So now I need to show you how to get this equation and what information I need to be able to do it. And this is the information you need. To find the equation of a line, in 3 dimensions, you need 2 things. 1, the coordinates of any point on the line. Just tell me any point. Find a point on the line, tell me its coordinates. I need to know that. And 2, what's called the direction vector. Direction vector V. And let's call that direction vector ABC. And let's call that single point on the line. X naught, comma, Y naught, Z naught. So can you imagine that I know this point here, and its coordinates are X naught, Y naught, Z naught. Its coordinates are 1, 2, 3, right? And I know the direction vector V. Can you imagine if you tell me a point in 3D space and you tell me the direction? Haven't you basically described what that line will look like? Right. If the tip of my finger is the coordinates of the point, and this pen represents the direction vector, don't I now know everything I need for that straight line? So an example of that. Suppose I tell you that a line passes through the point 1, 2, 3, and it has a direction vector of 1, -2, 5. What would the equation be? Well, the general equation is as follows. X naught plus AT, Y naught plus BT, Z naught. Maggie, you little demon. She switched off one of my lights. I don't know how she managed to do it, but she did it. There we go. So in this case here, the equation of the line will be 1 plus 1t, 2, minus 2t, 3, add 5t. Would you agree that's actually not that difficult to create? The coordinates, and then AT, BT, CT. Are we comfortable with how to get the equation of a line? It's basically that guy. Now, what's the equivalent to that? Well, in 2D space, if I tell you the coordinates of a point and its slope, isn't that enough information to get the equation of the line? Right. I tell you it passes through the point 1, 2 and its slope's 4. Can't you get the equation of the line with those? Right. Can you see that's like the 3-dimensional version of that? What's cool about this? Couldn't I extend this to 4 dimensions and it wouldn't really be too much extra work? Can I just say X naught, Y naught, Z naught, W naught? And the direction vector would be a 4th dimensional vector, right? 1, 2, 3, 4, whatever. Bump, bump, bump. Now here's some truisms about the equation of a line in 3D. This is the first one. Equation of a line in 3D is not unique. Right, do you know the one I've just done here? One plus t, why I keep doing that? 2 take away 2t, and 3 plus 5t. That's the parametric equation of the line. Nothing wrong with that, it's correct. But I told you the point P was 1, 2, 3. Couldn't I have found another point on the line that has a different coordinate? But wouldn't the direction vector still be the same directional vector? Let's say I kept that fixed. Now, can you just trust me that that point there happens to be, let's call it Q, happens to be 3, -2, 13. Now, if I use that one, wouldn't the equation of the line now be 3 plus t, -2 take away 2t, and 13 plus 5t, because this is fixed, but can't these change depending on who you tell me? You agree? Now, suppose I kept P the same. And the direction vector I just used was called 1, -2, 5. Wouldn't the direction 2, -4, 10, wouldn't that also be the same direction? Just twice as long doesn't stop it pointing in the same direction, right? And if I did this, can you see that the answer will now be 1 plus 2t, 2 take away 4t. Did I get? Yeah, 2 take away 4t and 3 plus 10t. Do you get that it's not unique anymore? Aren't all of these just different equations of the same straight line? Are we good? Right. Analogy here. Very often 3D straight lines, equations of 3D straight lines, are used to model objects moving in three-dimensional space in a straight line. Now, I've said t is like time. Do you know that this guy here is like your velocity vector? If these use big numbers, you're traveling along that line really fast. So if you find the magnitude of that, that's the speed that you're going at. So the direction vector is closely connected to the velocity of the moving object. Isn't that guy really where you start the journey from? It's just your initial starting point. So equations of lines can very often be thought of as movements in a linear direction, where the coordinate that you use is the starting point, and the direction vector is a measure of how fast and the direction you're traveling in. Very efficient modeling system. Very efficient. Okay, I've just overshot your time. Sorry for using up your time, because it is valuable. Say hi.